Alrighty. Hello, everyone. My name is Talen Niven, and today I'm going to be talking to you about how we can kind of start to decipher and solve what kind of compound we have based on only the only our proton NMR or our H NMR. So when we're actually solving these, what we want to look at is 1, 2, 3, 4, 5, 6 things, or 5 things, excuse me. And that is, first of all, going to be our signal number, just so we can stay organized. Then we want to look at the chemical shift. So that is where it is on this plane. So is it upfield, which is over here, or excuse me, is it downfield, which is over here, or upfield, which is over here. And then the integration. So that is usually going to be written right here, which is going to tell us how many hydrogens there are. The multiplicity, which is going to tell us how many neighboring hydrogens there are. And that can be seen through this kind of shape and then this kind of shape. And then finally, we're going to kind of draw a partial structure based on what we know about where it is and what it looks like. So let's go ahead and get started. This one we can see is, we already know is ethanol, but we're going to pretend that we don't see that. So we're just going to cross that out and then try to get there by ourselves. So on our spectra, we can see that we have 1, 2, 3 signals. And this doesn't mean that we're going to have only 3 hydrogens. This is just telling us that we have 3 distinct hydrogen signals. So 3 different hydrogens that are in chemically unique environments. So we'll go ahead and get started. So we'll start with number 1. So number 1, we're going to put right here, just so we can stay organized. The chemical shift, I would say, is about 1.1. These are always just kind of guesses. And then there's going to be P, P, M. And then we're going to look at the integration. So that has 3 hydrogens. The multiplicity, so we can see here that this is in fact a triplet because it has 3 spikes. So we have 1, 2, 3 different spikes within the same signal. So that's going to tell us it is next to 2 hydrogens. So it has 2 neighbors. And then a partial structure. This is most likely going to be a CH3 next to a CH2. So CH3, CH2, and then this can be anything. All right, so it's a good place to start. Now we're going to check our integration with the provided table. So as I said, we're about 1.1, 1.2. So what I like to do is I like to have a spectra or a table that I can draw on, because then it allows me to kind of get a little bit more specific with my lines. So I'm going to get a highlighter out right now and draw just about here. And it's hard to tell, but we have a line going right through here. So our options are going to be a CCH, or a CNH. Just kind of the options for that signal. So right now we're thinking that it's going to be a CCH. However, we're not positive yet, so it still could be a CNH. It's still a possibility based on what we know about the spectra. All right, so let's go ahead and work on number 2. So we have signal number 2. Chemical shift is about 3.6 ppm. It contains 2 hydrogens. It has a multiplicity, and we can see here. So it has 1, 2, 3, 4, which means it has 3 neighbors, 3 hydrogen neighbors, I should say. And then a partial structure, we're going to give that a second, just so we can check the table first. So like I said, it's going to be about 3.6. So we're going to zoom in here. We're going to be about right. Excuse me, let me choose black instead. Actually, I'll choose red. So we're going to be about right here. So let's look at some options for this. we have halides, which we don't have any evidence to support a halide yet. Alcohols could be a possibility. Esters could be a possibility. That just depends on whether or not we see a different stretch around here. But all of this is some good information. So I'm going to wait for this partial structure, even though it's likely that it's going to be kind of in the middle here. So I'll circle this one because that's where that one is. So we're looking, it looks like it's going to be CH3. Here's our CH2. And then maybe we're looking at an OH over here. So we're looking at this one. Oh, excuse me. Looking at this one because we know it has 2 hydrogens and 3 neighbors. So here it has 2 hydrogens and it has 3 neighbors. All right. Now let's look at, excuse me for a second. Now let's look at this final one. So we know it has 3 hydrogens. Excuse me, it's number 3. Its chemical shift is about 3.7. I would say, actually I want to say about 3.8. So we're saying about 3.8. Its integration only has 1 hydrogen, so it's just 1 hydrogen in that signal, meaning it has no identical hydrogens. We're going to look at the neighbors. We know that it is a singlet because it's just 1 peak, this little guy right there. So it has 0 neighbors. Now let's look at our data. So it says we're looking at about 3.6 to 3.8. So we're going to be very similarly in this range, just about right here. So I think it's going to be safe to say that we're looking at about either an alcohol or an ester once again. However, we are aware that there's on the exam or on the practices, you'll be given a chemical formula. So let me write that in right now. So we have, excuse me, it is C2H6O. So C2H6O. So we know that it's probably not going to be an ester or an ether, just because of the fact that we don't have that many carbons. We're not getting a distinct stretch. So we're probably going to be leaning towards alcohols. So we can go ahead and start putting together kind of an idea. So we know that this is not going to be an exact science just with this, because of the fact that we also need to incorporate IR and carbon NMR in order to distinguish the exact structure. But I feel like we have a pretty good idea right here because we only have 6 hydrogens, and this accounts for 3, 4, 5, 6. So we're going to go ahead and say that this is most likely our structure. And that we know in this situation because of the fact that it says ethanol at the top. So we're going to have boop, boop, OH. So that is our structure. And we know that because of the fact that it was given to us and we worked through the Proton NMR. So that was a pretty easy example. We're going to go ahead and get a little bit more complicated right here. So I'm just going to copy this table really quickly. And don't worry, I'll delete everything from it because we have to start fresh. So we're going to paste, move it to where I like it. That looks good. And I went ahead and erase all of the data from the first table. All right. So this is going to be a little bit more complicated. Let me pull up the structure for ibuprofen, just so we can get a kind of idea of ibuprofen. Want the formula? Ibuprofen formula is going to be C13H H18O2. And that is what we're looking at for ibuprofen. So once again, we're going to start by looking at how many signals we have. So we have 1, 2, 3, 4, 5, 6, 7, and 8. And as you can probably tell, 8 does not equal 18. So we're going to have, once again, equal carbon structures, but this time it's going to be a little different. So we're going to go ahead and start with signal 8 this time. Just work our way backwards from the highest to the lowest. So signal 8, we're looking at about a chemical shift of 11 ppm. Integration, we're going to look close. We know it has one, it looks like it has one hydrogen. Give me one quick second just so I can pull up. Yes, so I'm going to write in the integration right now because it was not included. So we have 1H, and it is a singlet, meaning it only has one peak. This one in its multiplicity, one peak in the multiplicity. This one is 2H and is a doublet. This one is 2H and is also a doublet. This one is 1H and is a quartet. So I'm going to put QU. This next one we have 2H and it's a doublet, so 2H doublet. This one is going to be one hydrogen and it's called a multiplet. And that means when we have a multiplet, we know that it's going to be more than 6 typically. And we're going to go here. It's going to be 3H, and it's a doublet, and 6H, and it is also a doublet. Okay, so this is more of what the exam or practices will look like. It'll actually show you the integration, but sometimes it does not show kind of the number of peaks that are given, but most of the time we will see that when we're trying to decipher. Okay, so we'll go back here. We're still working on number 8. The multiplicity is a singlet, which means it's going to have 0 neighbors. We have a lonely boy out here, and then we're going to check our spectrum. So we know that we're at about 11, and 11 makes it pretty clear what we have. So it could possibly be an aldehyde, but this will be seen in the IR. But we're really it's pretty clear that we're going to be looking at a carboxylic acid. So this is going to be the C double bonded O, and then we have OH. Here's an R group. So we're going to look at this. Is going to be looking at this hydrogen, and this is just a guess. As we all know, the partial structures are usually just guesses, and then we can kind of work everything together towards the end. Okay, let's continue. We'll work on signal number 7 and number 6 are very similar. As we can see, they're almost in the exact same place. One is just slightly more downfield than the other, but they're going to be pretty similar to look at. So they're both going to be at about 7.1 to roughly 7.2 ppm. Oh, excuse me. ppm. So they both have 2H, and they're doublets, which means each hydrogen is next to only one neighbor. So 1, 1. And multiplicity can often be confusing. I like to use kind of just a formula, and that's going to be number of peaks or hydrogen, that's an ugly H. So hydrogen is equal to number of peaks minus 1. So once again, here we're going to see kind of 1, 2, 1, 2. So minus 1 is going to give us 1 neighbor hydrogen. So we're going to look at our data once again. So we're looking at 7.1, 7.2. So we're going to be sitting right about here. And although we have a bunch of options for this, kind of the most distinguishing one, or the one that's easiest to identify in this region is going to be aromatics, because of the fact that we have 1, 2, 3, 4 identical hydrogens. So what that means is we're most likely going to see a benzene. So this one is going to be encompassing 2. So what we're going to see is a benzene, R group, and another R group, because that'll give us these two will be identical, and then these two will be identical, giving us 2 peaks. Each hydrogen is only next to 1 neighbor. And yeah, there's 2 at each location. So this lines up perfectly with signals number 6 and number 7. So now we're going to keep on moving down. We're going to go to number 5. Go ahead and take a look here. So this is actually super helpful because it gives us a little zoom in right here. This is number 5, 4, 3, 2, and 1. So this just kind of zooms in on this whole area, making it easier to see the number of peaks. So for number 5, we know we have down here, we know we have a peak at about 3.8 ppm. We have 1 hydrogen in that location, and it is next to, it is a quartet, meaning it is next to 3. So it's 3 neighbors, 3 hydrogen neighbors. And now we're going to look over here once again. So we're looking at almost 4, 3.8, pretty close to 4. And we're looking in this region right here. Let's go ahead, give it a quick draw. All right, so we know that we have our alcohol. However, So we know that we have our alcohol. However, we know that this hydrogen is going to be by itself right here, and it will not have 3 neighbors. It's actually going to have 0 neighbors, as we wrote here. But we also have kind of alcohols and esters in this. So what we're going to be looking at is something around here, maybe a hydrogen around there. So I'm going to go ahead and leave this structure just because it's going to be hard to determine right now. But it's likely 1 hydrogen. So it's going to look like that. It's going to be CH next to a CH3. That's likely what we're going to be looking at for that one. It's going to be pretty de-shielded, meaning that something is close to it is very electronegative. So let's take a little tangent right now and talk about some de-shielding. So let's say we have oxygen next to a hydrogen, and it's next to carbon, and this carbon has 3 hydrogens. So we know that oxygen is pretty electronegative, which means it's going to pull electrons towards it. So we know that this hydrogen is going to be incredibly de-shielded, which means kind of the electrons are going to be preventing it from so electrons, when they are in NMR, when there are electrons around an atom, it's going to kind of protect it, which means it'll be more upfield, and upfield once again to the right, downfield is to the left. So when a proton is next to a very electronegative atom, it's going to pull the electrons away from it, making it less stable and go further upfield. So not only does this oxygen pull electrons away from this carbon and this hydrogen, but also affects these hydrogens as well. Oh, that is horrible. I'm so sorry. Affects these hydrogen as well, which means these hydrogens are going to be more likely to be closer to this oxygen, further deshielding this carbon and all of those hydrogens. So that's just a little tangent, just to kind of explain why things are going to be downfield versus upfield. Yeah, so now we're going to go to number 4. Number 4 has a chemical shift 2.5, roughly. So we're going to say roughly 2.5. And zoom back into number 4. Let's see. We have 2 hydrogens there. And it is a doublet, meaning it has one neighbor. So if it's going to be a 2 next to a 1, it's probably, we'll check this out first. So we're looking at 2.5. So we have a ton of options here. So all of these are going to be solid options. However, I'm going to be leaning towards kind of the alkenes. And yeah, so these alkenes are going to kind of be what we're looking at. We're going to kind of draw just an idea. So we know that we have 2 hydrogens with one neighbor. So we're going to have C, H, H, H. It's next to a carbon here. Maybe it's a double bond to an O. Just kind of an idea. And this would have, excuse me, this would have hydrogen on it. We're looking at these 2. This is just kind of an idea. We're not entirely sure about that one right now. So now we'll go ahead and look at number 3. Might have to extend these lines a little bit. I'm just now realizing how crooked these are, but it doesn't have to be pretty as long as you guys can understand yourselves. So once again, we're looking at signal number 3, and we're looking at just about 1.8 on that one. So when I say roughly 1.8, and none of these are exact, these are just kind of estimates, which is why they have the squiggles in front of them. So at 1.8, we're going to have 1 hydrogen that is next to 3 hydrogens. So it's going to be 1H, and it has a multiplet, or excuse me, it's not next to 3 hydrogens, it's next to multiple. So we're looking at many. Yeah, and this kind of follows what we had up here. So we're going to be looking for 1 hydrogen, so it's going to be a CH. It's next to many neighbors. So at least 7, at least 6 or more than 6, so at least 7. So we're going to have an R group up here, which likely has a hydrogen, and then we'll have CH3s here. And this shows that we have 3, 6, 7, which would produce a multiplet, and there's only 1 right here. So this is a pretty good idea for that one. I'm going to make it a little bit smaller just because she's taking up a lot of space. Now we're going to go ahead and look at number 2. So we have number 2 right here. Number 2 is 3 hydrogens in a doublet, so it's next to 1. So, oh, excuse me, I forgot to write the shift. So that is going to be about 1.5. I'm just finishing up labeling these because I forgot to earlier. Okay. So we know it's 1 hydrogen. Excuse me, it's 2 hydrogens. Is it the case? No, final answer, it's 3 hydrogens. So it's going to be 3H next to, it is a doublet, so it's next to 1 neighbor. So that's probably a CH3, just a methyl group on the end. It's going to have a CH3 with a CH right here. Just kind of an idea. So that one's going to have that many bonds. So it's 1, 2, 3, 4, because carbon always wants to form 4 bonds, excuse me. And then we'll finish up with number 1, which has a shift of probably 0.8, 0.9. We want to see 0.9. We know that 6 hydrogens. So we have 6H. It is next to 1 hydrogen because it's a doublet. And so this probably looks like, this is going to look like our 2 methyl groups in the end right here, but I'll redraw it out. So you have CH3, CH3 together that have 1 neighbor. It's going to be CH. It's going to be right here, CH, and then further up there. So we've gone through the structure. We can see that it's pretty complicated. We're just going to start taking guesses. So we know that we have a benzene. I'm going to draw it further down here. So boop, boop, boop. One of my favorite things about doing electronically is it makes my hexagons look much nicer than I could ever make them. So we're going to have our benzene. We're going to make sure it's aromatic. And then we're going to have a group up top and a group down the bottom. So right here is satisfying. There's a hydrogen here, hydrogen here, hydrogen here, hydrogen here. So that looks good so far. We're going to move on, and we know that we kind of have we're going to have our OH or carboxylic acid somewhere, either up or bottom. We'll go ahead and draw it on the top. So I'll just do COH somewhere over here, and we'll start going through these alkene bonds. So the one that really sticks out to me is going to be these. So we'll go ahead and kind of just do boop, boop, boop. Excuse me. So here we have 1 signal, 2, I'll do this in another color actually. So here we have 1 signal, 2 signals, 3 signals, nothing here, 4 signals, 5 signals, 6, 7. So we are short a signal, which is interesting. But we know that there has to be more to this. There's more to the structure. This is a pretty good start. I'm going to head and erase the COOH. I'm going to put a bond right here. COO. I'll draw it all the way out actually. So we have a double bond there. Looks beautiful. I lied, it doesn't look good at all. Let me fix this a little bit. Double bond right there. There we have an OH. Okay, so it's looking a little better. So we are going to have an issue with this one because of the fact that this is going to be a CH2 and is next to 0 neighbors, but we don't have anything like that. What we do need is we need to have a CH that is bonded to a CH3, which is this one right here. So we need to include signal 5, which we don't have yet. And we know that it'll be pretty far downfield because of the de-shielding that I talked about earlier. So we're going to see if we can draw a methyl group right there and see if it works better. So now let's look at our signals. So we have 1 signal right here because they have identical chemical environments. 1 signal right here. 1 signal right here. 1 signal right here. 1 signal right here. 1 right here. 1 right here. And 1 right here. So we have 1, 2, 3, 4, 5, 6, 7, 8. So far we're looking good. We'll just go ahead and double check everything. So we're going to go top to bottom and look at all of our signals. So at number 8, we are looking for carboxylic acid that has 0 neighbors. So here we have a hydrogen on the carboxylic acid, and here there are no neighbors. So that one checks out. We'll go ahead and cross it out. Excuse me, cross it out. So now we'll look at number 7. 7 is going to be 2 hydrogens that are bonded to 1 neighbor. Okay, so we'll look here. Let's see what we have. Yeah, so 7 and 6 are going to be the same. It's going to be this one. will be the more downfield because it's closer to the withdrawing group, electron withdrawing group. And then this one is going to be the lower of the two. So that means this one, I'll just label it. This one is going to be signal 7. This one's going to be signal 6. Go ahead and cross those out. Boop, 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 boop. Next, we're going to be looking at signal 5, which is going to be 1H with 3 neighbors. So this one we already talked about is going to be right here. There's going to be 1 hydrogen, little guy right there. And that is going to be signal 5 because it's next to CH3, our methyl group, and it's 1 hydrogen. So it's looking good. Now we'll go ahead and move on to signal 4, which is going to be 2.5 ppm, 2H next to 1 neighbor. So it's 2 hydrogens that are next to a single neighbor. And that is going to be right here. So we're going to have boop, hydrogen, hydrogen. There's going to be 1 hydrogen right here. So these 2 hydrogens are next to a single neighbor because this one is full. So we're going to go ahead and make sure that looks good. And we're going to label it. So that is number 4. 4. Okay, so we'll go ahead and cross 4 out. We're getting close here. We'll look at signal number 3, which is 1 hydrogen that's next to many neighbors. That one is going to be the one we just drew right here. So we can see that this one has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. So that we got this one would be a septet. So it'd have 7 bumps. So we will go ahead and label this one as number 3. Number 3. Okay, we'll go ahead and cross them out. Number 2 is going to be 3H next to 1 neighbor. So we're going to look up here. As we can see, we have 3 hydrogens that are next to a single hydrogen neighbor. So that one's going to be number 2. And finally, last but not least, we're going to check this one because this is our last signal. As we know, these two CH3s see the same chemical environment. So we have 1, 2, 3, 4, 5, 6, and they are next to 1 hydrogen. So we'll go ahead, we'll work backwards this time. So when we're looking for 6 hydrogens that are next to 1 hydrogen. So we have 6 hydrogens, they're next to 1 hydrogen, which means that this is likely to be our structure. And like I said earlier, this is going to be a little bit more difficult when you're on your own because of the fact that right now we are only working with IR and or just the proton NMR instead of IR and CNMR as well. So it's going to be a little bit harder to tell. It's actually going to be, I think it'll be easier because we will have information on each carbon as well as each of the functional groups, which is helpful. But I hope I helped you learn something today. And here is going to be our final spectrum, our final drawing structure for ibuprofen. Yeah, thank you guys so much for your time. And I hope you enjoyed.